Hello, this is part of the Controlled Environment Plant Production Engineering / Technology Education modules that were developed and presented by the Ohio State University, Rutgers University, and the University of Arizona, with support from the USDA NIFA program. The learning objectives include for you to be able to understand the design differences between natural and mechanical ventilation systems and to calculate design characteristics for natural or mechanical ventilation systems. Additional resources include the American Society for Agricultural and Biological Engineers, their engineering practice EP 406 that was published in 2003, as well as the book by Aldrich and Bartok titled Greenhouse Engineering. When you think about temperature control and ventilation, you have to think about photosynthesis first. Here I show you the equation of photosynthesis, and I want you to remember that this process is temperature dependent. So we need to control the temperature in a greenhouse to make sure that we optimize the process of photosynthesis, to optimize plant growth. The purpose of ventilation, as well as the purpose of cooling, is to control the temperature to make sure we provide the optimum conditions for plant growth. We also want to do moisture control. We want to bring in fresh air. As you know, plants produce oxygen and take up carbon dioxide. So as that process is going on, we want to make sure we bring in fresh carbon dioxide and perhaps remove excess oxygen. We want to keep insects out as we are moving air through the greenhouse for the ventilation system to control the temperature. We could potentially bring in insects, and we want to try to prevent that. And overall, we want to control the climate for the plants, not only the temperature, but humidity and perhaps gases, CO2 and others. We do that for the plants primarily, although sometimes I've seen greenhouse operators do that for humans, the people that work inside as well. The question is that a smart strategy? And typically I recommend look at the plants first and then look at the people, although sometimes it's the other way around. So the general features that we find in ventilation and cooling systems is that we displace and condition the air that's involved in this process. We can do that with a mechanical or a natural ventilation system. In a mechanical system, we use fans, mechanical fans that are driven by electricity, by electric motors, to produce the right temperature, and we can use fan staging to reduce the overcooling and provide additional energy savings. So by staging the number of fans we run in a mechanical ventilation system, we can make sure we always provide the right amount of ventilation. We don't overventilate, we don't underventilate. Mechanical ventilation can be combined with evaporative cooling systems. The evaporative cooling systems that I'm talking about is mostly the pad and fan system. And it can be operated under positive or negative pressure systems. That means that we either suck air out of the greenhouse with the mechanical ventilation system, so we create a negative pressure, or we can push air into the greenhouse to create a positive pressure system. And the latter system is typically used for greenhouses where we are concerned about insect infiltration. If we create a higher pressure inside the greenhouse, then it's more difficult for the insects to move upstream and to get into the greenhouse. And then another feature of cooling or venting is a shading system, of course. By using a shading system, we can also reduce the temperature inside a greenhouse. We reduce the heat load that is perhaps causing plant stress, heat stress. Here's an example of a different ventilation system, both a natural and a mechanical. The natural ventilation systems are shown in the top two pictures. On the left-hand side, a freestanding greenhouse with side vent openings and ridge vent openings. So air can enter on the side wall through that opening and then escape from the ridge. The warm air inside the greenhouse will rise to the peak and exit there and creates a nice flow pattern that hopefully provides uniform ventilation throughout the house. Another ventilation system are the Dutch Venlo greenhouses that typically only have vent windows in the roof, and depending on the location of the window, the prevailing wind direction and the wind strength, those vent windows can act as inlet openings or outlet openings, or perhaps even as both an inlet and an outlet opening, depending on the pressures and the airflow created at that location. The bottom two pictures show a mechanical ventilation system with, on the left-hand side, in one end wall, a row of fans, again driven by an electric motor, and on the other, the opposing side wall, we have a large window that opens up to allow air to enter the greenhouse when the fans are operating. Discussing natural ventilation in a little bit more detail, these systems can be used for greenhouses as well as screen houses, so greenhouses that are just covered with a screen, as we see in some tropical or subtropical climates. We don't use fans to draw air through the greenhouse with these systems, but we use two different physical processes to move air. The first one is called the stack effect or thermal buoyancy, and that means that warm air is less dense than colder air and thus rises up. Think about the stack in the chimney in your fireplace at home. And we make use of the wind effect. The wind is almost always blowing around structures. It's hardly ever completely wind still. And those air movements related to the wind blowing create small pressure differences on the windward side and on the leeward side. And by positioning ventilation windows strategically, we can make use of those pressure differences to move air through the greenhouse. The wind effect is typically the dominating force. As long as the wind is blowing at more than 200 feet per minute or about 2.3 miles per hour, which is not very fast, then the wind effect dominates. So only under very wind-still conditions will the thermal buoyancy or the stack effect have a major impact on the ventilation rate. Natural ventilation systems are typically not combined with evaporative cooling pads because there is too much resistance for the air to overcome that pad that is installed in the ventilation opening. So we have to find other means, such as a fogging system, to cool the greenhouse down with an evaporative cooling approach. This image shows some ventilation windows installed in the roof of a greenhouse. Again, these are naturally ventilated greenhouses. And if you look carefully, you see that these inlet openings are all screened with an insect screen. The insect screen is necessary to try to keep insects from coming into the greenhouse. However, the insect screens add resistance to the airflow as it moves in. And that's why these insect screens are mounted in an accordion shape to try to increase their surface area. By increasing the surface area, we reduce the overall resistance to airflow. And so we can still screen the ventilation openings by adding more surface area, and then the added resistance is not too high to prevent sufficient ventilation rates. An extreme case of natural ventilation is the open roof greenhouse, where the entire roof opens up, allowing for lots of air exchange between the inside and the outside. And as a result, we see temperatures inside the greenhouse that are virtually identical to outside temperatures, which is very difficult to do with traditional natural ventilated or mechanically ventilated greenhouse structures, because the amount of air exchange necessary to accomplish the same temperature inside as well as outside, particularly on hot days, is very significant. So with this extreme ventilation option, by basically opening up the entire roof, we have a lot of air exchange, and we are able to accomplish virtually identical temperatures between the inside and the outside. Discussing mechanical ventilation systems in a little bit more detail. We have to worry about fan parameters, for example, the capacity. How much air is that fan able to move? Typically, we use cubic feet per minute as the metric to express the fan capacity. We need to know what resistance that fan can overcome to push that amount of air through the fan. And so we typically identify that as the static pressure, and the unit of measure is inches of water. And typically fans are rated by an independent testing laboratory based on a set of guidelines that was developed by by AMCA. And when fans are rated like that and checked and confirmed that indeed at a certain static pressure they were able to provide a certain flow rate or capacity, then they get a sticker indicating that they passed the test. So when you think about buying fans for greenhouse ventilation applications, you want to make sure you buy a fan that was tested properly, and the result of that test are indicated by the AMCA sticker that you will find on the fan when you purchase it. Another parameter of the fan that's important is the ventilation efficiency ratio. So how much airflow is the fan able to provide for the unit of electricity in watts that you're able to, that the system requires to operate. So how efficient is the energy conversion? And finally, what is the power requirement? So how many horsepower does the motor require to operate the fan? So all these parameters are important to understand and to know before installing a fan system in your greenhouse operation. The inlets are also critical, and we have different designs. We can have continuous windows that we open up, or we have openings that are louvered. So as soon as the fan comes on, the louvers will tilt open, allowing air to come in. These openings should close tightly when the fan is not in operation, because these openings might allow for lots of infiltration and thus heat loss when the fan is not running. And typically, for mechanical ventilation system, we need 1.4 square foot of inlet opening for every 1,000 cubic feet per minute of fan capacity that we install. So with this number, you can approximate how much opening area you need given a certain overall fan capacity that you install in a mechanical ventilation system. Most fans are equipped with louvers to shut off when the fan is not running. We typically prefer to have those louvers installed on the inside of the fan housing, so on the upstream side of the fan, and that is so as to reduce the resistance of airflow throughout the entire fan system. And they should obviously close tightly to reduce energy loss, as I mentioned before. When you think about sizing the exhaust fans, we have two conditions that we need to worry about. The first one is the maximum ventilation rate needed for summer conditions, and the other one is the minimum ventilation capacity needed for winter ventilation. So let's first look at the summer conditions. Depending on whether you have a shade screen installed to reduce the heat load on the plants and to the inside of the greenhouse, you have different rates that we recommend. And if you have a evaporative cooling installed, that typically means you need more force to pull the air through the evaporative cooling pads. If you have pads installed, then you need to further increase the overall recommendation for airflow rate per unit of floor area. So for a shade screen, you typically need 8 to 10 CFM, cubic feet per minute, per square foot of floor area of capacity. So once you figure out your greenhouse area, you can then calculate what the overall fan capacity should be for maximum summer cooling. And then if you have no shade screen, we need to up that a little bit. If you add an evaporative cooling system, we need to further up that number to make sure you get the right airflow rate through your system. A note of caution, in the past many people used the 1 air exchange per minute rule. In other words, they wanted the greenhouse to exchange its entire volume once every minute, and based on that they calculated the ventilation requirement. Since we are building taller greenhouses, that would indicate that using this rule we would have to have more and more ventilation capacity. That, however, is not correct, because the main heat load that requires us to ventilate a greenhouse is coming from the sun, and the sun of course radiates per unit area, unit floor area, and so the 1 air exchange per minute rule is not appropriate for this type of calculation. We further need to make some adjustment for special conditions. If your greenhouse is located at a higher elevation, we need to make an adjustment. We need to have a conversion factor or an extra factor in the calculation to make sure we get the right ventilation rate. If the light intensity is very high, again, if you are in a very bright environment where you get a lot of sunlight, we want to further increase the ventilation rate. If you want to maintain a temperature change from the inlet side to the outlet side, and you want to maintain the temperature change in a relatively small amount, we need to further increase the ventilation rate as well. Because if you think about a ventilation system, there's going to be a temperature gradient from the inlet side to the outlet side. As the air moves to the greenhouse, it picks up more heat, and thus the temperature will change. If you want to have that gradient as small as possible, we need to start moving more air to the greenhouse to make that happen. And so there are certain adjustments that I show you on the bottom of the slide here that we can make given certain special conditions that you may have for your particular application. So look at those and include those in your calculation if they apply to your situation. The next slide shows you what the recommendation is for the minimum winter ventilation rate. We still need to bring in fresh air in the wintertime, perhaps not for cooling purposes, but to make sure we have enough CO2 in the greenhouse, and we need to reduce the moisture level in the greenhouse. So the recommendations are to go with maybe 10 to 15% of the maximum cooling capacity that we calculated for the summer conditions. And so you can see here what that number comes down to, depending on whether you have a shade screen installed or no shade screen installed. So after you made those calculations, you have your maximum cooling capacity requirement, you have your minimum cooling capacity requirement. You can then go to manufacturers' published data, their brochures, and look at different capacities and different sizes and different static pressures they're able to overcome. And you can start making selections. You can start figuring out what's fan size and how many of those fans you want to install in your greenhouse operation. You want to make sure you pick a fan that is able to deliver the required ventilation rate at a certain minimum static pressure, and we typically use a number of 0.1 or 0.125 inches of water gauge as the minimum static pressure that the fan needs to be able to overcome. You can use a higher static pressure if you also install insect screens, because they add additional resistance to airflow through your structure. We want to make sure we install those fans after you've identified them and purchased them evenly across the growing space. We want to make sure that we don't get channeling of air as the air moves through the structure, so we want to evenly distribute those fans throughout the structure. And then we want to use fan staging, where, for example, the first ventilation stage only provides maybe 10% of the overall capacity that you've installed. The second stage perhaps 40%, and the final stage 100%. And the reason the staging is not symmetrical, so we don't go 10, 50, and 100, is that we are able, by this non-symmetric fan staging, we're able to provide better the right ventilation rate needed for the conditions that may occur in your greenhouse operation. So fan staging becomes also an important issue. This is less of an issue when you have variable speed controls on your fan motors, because now you can dial in exactly the correct rate. But if you have fixed motor speeds, then the staging becomes important to try to best match the required rate to your fan installation. The next slide shows an example of an insect screen installed with a mechanical ventilation system. I mentioned already that the insect screen adds additional resistance to airflow for the ventilation system, and so in this particular greenhouse they installed an entire addition to the greenhouse outside the side wall that houses the ventilation opening, the window, and they made the entire vertical section of this extension, they covered that with screen material. So the reason for doing that is that you add additional surface area for your screen and thus reduce the overall resistance to airflow. So by maximizing the screen surface area, you minimize the resistance to airflow, and thus your ventilation system is able to pull sufficient amounts of air through the greenhouse. If you didn't do that, if you made the screen smaller, you would increase the overall resistance and you would reduce the ventilation rate, and you may not get the proper rate to maintain the set points inside. So how do we size these inlet openings? We typically, as a rule of thumb, require that the inlet air velocity is at least 700 feet per minute. And the reason for using this number is that we want the air to come in with a fair amount of velocity, with a fair amount of momentum, so it mixes properly with the air already in the greenhouse. So by giving it a fair amount of speed, a fair amount of momentum, it mixes better before it actually reaches plant level. And when you use this number, you realize that you need 1.4 square feet of inlet opening for every 1,000 cubic feet per minute of fan capacity that you have installed. There's different types of openings that we use. We can have louvered shutters, we can have continuous windows, we can have sidewall openings, and we can have roof openings. Here you see an example on the upper left-hand side of a sidewall window that opens up. This one is not screened. Or you can see on the lower right-hand side a picture of a set of louvered inlet openings. So the fan, in both cases, the fans are both not visible in these pictures, but are installed in opposite end walls. And then as soon as the fans come on, the windows or the louvers open up to allow fresh air to come into the greenhouse. The control of these openings can be done differently. We can have manual control, which is relatively inexpensive but requires somebody to make adjustments continually or fairly often, which can be tedious and takes a person away from other duties. An example of manual control is, for example, using roll-up sidewalls in high tunnel structures or hoop houses. We can also motorize ventilation openings, and typically that means that a computer system is involved that directs the motor to open or close the window. We can do this by a fixed opening. In other words, as soon as the fan comes on and at a certain stage the motor brings the window to a certain size opening, to a certain fixed opening, or we can have adjustable opening strategy where we use a differential pressure sensor to sense the differences in pressure that is generated by the fans as they're running, and then based on the settings we try to maintain the right inlet velocity of the air coming in. So the pressure sensor senses the difference between the negative pressure inside the greenhouse that is generated by the suction of the fans, and it looks at the outside pressure, and based on those two pressures it opens and closes the window to just the right location so that the airspeed of the air coming in to the greenhouse is at the right velocity so that that air mixes properly with the inside air. We can do that with a differential pressure switch that measures these pressures continuously and then drives the motor to open and close the vent window to make sure that pressure difference is maintained between the ranges that we told it to maintain it at. It's very important to remember that when you do this type of ventilation control, you have an airtight greenhouse so that the ventilation occurs only where and when it is desired. We don't want ventilation to occur through other cracks than the window that we open up because that would disturb the patterns and it would perhaps occur during times when we didn't want ventilation. For example, when you're concerned about infiltration heat loss, when you think about heating and cooling greenhouses. Here's an example of such a differential pressure switch. In this case, the switch is trying to maintain a pressure difference between 0.05 and 0.1 inches of water gauge. So as soon as the fan comes on, so as soon as the sensor indicated to the computer control system that the temperature was too high, and as a result the computer system turned the fan on, suction occurs inside the greenhouse. It creates a pressure difference between the outside and the inside, and then this switch is then controlling the motor that operates the ventilation window opening to try to maintain a certain pressure difference. And by maintaining that certain pressure difference, we can guarantee the proper air speed of the air coming in that then results in proper mixing of the air coming in with the inside air inside the greenhouse. This is particularly important in the wintertime when that air coming in can be relatively cold and you don't want that cold air to hit your plant material before it has a chance to heat up and equilibrate with the rest of the greenhouse air. Another trick that a grower was using to try to prevent cold stress on plant material is this greenhouse where you see a grower put a plastic barrier of maybe 1 or 2 feet high between the inlet and the location of the plants, which were grown on the floor in this case. So think about winter conditions. Air is coming in from behind the evaporative cooling pad. You can't see the window opening, but it's behind the cooling pad in this picture. It goes to the cooling pad, and because the air is cold, it falls directly on the floor and would then be dragged across the floor to the other side where the fans are located. But by installing this vertical barrier of plastic film, the air was forced up again, mixing it more properly with the greenhouse air before it was allowed to enter the area where the plants were grown. The control we are doing, temperature control in greenhouses, we can do with thermostats. For example, we can set different day and night temperatures with different thermostats, and based on the reading of the thermostats, we would engage the ventilation system or the supplemental or the heating system or the cooling system. Or we can do it with a computer system where we have a control algorithm that we can program that then tells us exactly, based on the measurements that the system receives, what we need to do, whether we need to heat or whether we need to cool, and things like that, whether we want to close the curtain system, whether we want to run the lighting system, etc. The goal of temperature control is typically to work with the smallest possible deadband. And the deadband means the allowable temperature range that we use without equipment intervention. And what I mean with that is when you think about controlling the temperature in a greenhouse, let's say we want to control the temperature at 70 degrees Fahrenheit. If the temperature dropped below 70 degrees, we would turn on the heating system, and if the temperature was above 70 degrees, we would start a ventilation system to maintain our target set point. But if you did that, then you would have the equipment operating or almost fighting each other. You would have the fans running a little bit, and then you would have the heating coming on, and then you would have the fans running a little bit, etc., to try to maintain a steady 70 degrees. So what we typically do is we allow a deadband in which we do not operate any of the control systems. So let's say the deadband in our case would be from 69 to 71. So only at 71 degrees Fahrenheit would we start cooling the greenhouse, and at 69 degrees we would start heating the greenhouse. And we do this to try to minimize the back and forth between the various control systems that we use to maintain the proper temperature. And so the trick is to have the smallest deadband that is allowable to maintain the temperature without having the systems fight each other all the time to maintain the proper set point. We obviously want to reduce overshoot of the set points as much as possible. So we don't want to engage the heating system to try to get back to the 70 degrees Fahrenheit and then have the heating system overshoot and end up all the way at 72 or 73 or 74. So we want to try to shut off the heating system long before things tend to overshoot, to try to save energy as much as possible. We obviously want to minimize the equipment cycling as much as possible because that has a negative impact on the longevity of the various systems we use. And one of the ultimate goals is, of course, to minimize energy consumption. So temperature control, although it sounds easy, can be relatively complicated and includes many different aspects of control strategies for proper implementation. We also need, of course, temperature sensors. We need the system to know what's going on. So we need reliable sensors. We need sensors that are accurate and repeatedly give us the right measurement. We typically recommend that sensors, and especially temperature sensors, are installed in so-called aspirated boxes so that we shield them from sunlight and we shield them from any moisture that could fly around when people are watering plants, so that sunlight will not have a negative impact on the measurement that is then reported back to the control system. So the aspirated box means it is a box with a little fan that draws air through and past the sensor, and that gives us a good average measurement of the conditions inside the greenhouse. We want to put that sensor at a representative location, so we don't want to put it somewhere near a door or near an end wall. We want to put it somewhere that represents the conditions very well, and we want to put that sensor near the plants. We don't care too much about the temperature near the floor or in the peak of the greenhouse, near the roof of the greenhouse, when the plants are grown on benches, for example. So you want to put it where we get a good representative measurement as well as where the plants are located. The picture on the bottom shows you here what not to do. On the left-hand side you see a row of thermostats that are not aspirated and are exposed to greenhouse conditions and are installed a certain distance away from the crop. In this case that was grown on the floor of the greenhouse. So the temperatures are not aspirated, not shielded, which could mean that if the sun comes out and shines directly on these sensors, then they give you a false reading. So on the right-hand side you see a proper installation, a little aspirated box. You see some fans or gills on the side. The fan is located at the bottom. It's drawing air through the gills, past the sensor, and then out the bottom of the sensor housing, so that you get a good representative measurement in your system. We'd like to acknowledge the funding that was received for this effort by the USDA NIFA program.